In this video, we begin discussion about rendering our objects using a concept of light. Up to this point, we use some solid colors as part of the vertex attributes loaded into the GPU, or we also tried some eccentric ways of computing a color, like using normal vector coordinates as color components. However, to make objects look like real 3D shapes with realistically lit surfaces, we will be modeling the interaction between the light falling on the surface of triangles and add more realism to the appearance of our objects. So this is our presentation. Directional light appears like it's coming from a light source which is located really far away, like sunlight, and therefore it's having the same direction for every point on the scene. So using directional light simplifies math because we only need one single vector that will give us the necessary information about the light. Another type of light is a point light. The light source must be positioned itself somewhere in the world coordinates together with our objects. An example might be a street light or a ceiling lamp inside a room or headlights of a car. So there we must compute a vector that connects every fragment or every pixel with the location of the light source. Obviously, the light position itself may change in every frame of display because the light source could be moving. An idea of a lighting model is that we decide to compute a certain algorithm, like a mathematical function, which will determine how a surface interacts with light. We have to use this mathematical function for every fragment if we compute our lighting model inside a fragment shader, or if we're computing the lighting model in a vertex shader, then we have to execute this function for every vertex. Ambient illumination simulates light reflected from the environment. So we have seen an example of ambient light in the previous laboratory exercise, where we try to give every pixel certain illumination intensity. If only ambient light is used on a model of our object, it will appear as a silhouette. So ambient illumination is based on a minimal color an object emits when no light is present at all. So for us, this is an easiest light component to implement because we just decide each color component and we can assign it to every fragment. Diffuse light shows how the light bounces off of the surface of an object in all directions. In OpenGL, diffuse lighting is calculated from the relationship between the light direction and the normals of the object surface. For example, if we take this pixel somewhere here on the surface of this object, this teapot, and we say that this is our normal vector pointing perpendicular to this place on the surface, and our light source is located somewhere here. Okay, so this is the vector that connects this pixel with the light source. So then if we normalize these two vectors, right? So if this normal vector is already a unit size, and we also normalize this vector so it also computed as a unit size vector, then we can calculate diffuse light intensity as a dot product between these two vectors for every vertex in the vertex shader, or for every fragment if we're doing this computation in the fragment shader. And of course, if we're taking dot product of these two vectors, then the result, in case if the two vectors are normalized, the result will be just a cosine of this angle, which means that if the light source moves over here, and so if the light source is somewhere here and the angle between these two vectors is close to 0, the cosine of small angles will be close to 1, which will give us the highest intensity of illumination. Otherwise, if this light source is moved somewhere here and the angle becomes close to 90 degree, then the cosine of 90 degree will be 0. So the intensity of illumination will be minimal or none. And in a case like this, when the light source is here, to eliminate total darkness, we basically combine the ambient level of light with diffuse light based on a dot product. And this combination should give our object an appearance of certain material that it's made of. A specular light illuminates the shiny spots on objects with smooth surface. So the size of each shiny spot is controlled by the shininess. And the higher the shininess, the smaller the shiny spots will be. The specular highlights correspond to how hard or how soft and smooth the material will appear to the viewer.